basically we're gonna have another, so including this chapter, we're gonna have another 5 chapters to be covered for the semester, right? And also remember that in the first class, all right, of the semester, I mentioned that you need to do a presentation, right? Presentation as 5% of your carry mark. Okay, so for that, actually, you need to make a presentation, okay, on the how you could perform, okay, physics experiment. So regarding about what you have learned so far, all right, and then you need to relate that with the related theory on that. Okay, so basically you need to use whatever it is available at your home, all right, and then make the experiment by yourself, all right, and then prove that with the physics theory. I mean, maybe you need to use you must use the equation, right? You must use the equation inside the physics and then try to relate that. So I want to see, I mean, in terms of your creativity on how you can do that, all right? So just use whatever it is at your home, right? Or if you don't want to use whatever it is at your home, maybe you want um, to buy it outside, okay, the materials, whatever. It depends on you, all right? So as long as you can prove that physics theory is related to that experiment, that should be fine. Okay, so that actually 5% of your mark, if I'm not mistaken, I need to refer back. Okay, so for that presentation, you're going to do that in the week 14, all right, in the week 14. So now it's week 10, so you can prepare that from now. Uh, so if you need further clarification, um, you can ask me later. Okay. So basically prepare for that for week 14. So basically the for the uh we're going to start that on Monday. All right, on Monday week 14, we're going to start that on Monday, and then for that presentation, all right. So basically, you can have two pairs, all right. Two of you can pair together. So okay, so you can make a group of two. Okay, so you can make a group of two, and then um, you can, yeah, make a group of two, and then for each of the group, make one physics experiment. Okay, and then prove that with theory of the physics that you learn during this course. Okay, so that's it for the presentation. Okay, so today we're going to continue with the chapter 15, which is the mechanical wave. Okay, so basically this experiment you have done before, okay, about the mechanical wave, about the interference or standing wave, okay, and about the frequency as well. So as you can see that the wave is related with the vibration, okay. So for example, here we have the earthquake, okay. So earthquake is actually one of the wave, okay. It's actually the wave that moves the inner core of the earth, right? So when that vibrates, so when the interference between that, so can be something something big, okay. Okay, so for example, we have also another wave, right? Such as the vibration, the string of piano, okay. So that's why you can see that when both of the waves are what we say that interference, co-interference, then they will overlap each other. So you see that the wave overlap each other. So you make a bigger amplitude of that. So that's why you see that the energy or the sound, okay, the sound of that is much louder than before. Okay, so because that is the interference of the wave. Okay, for example, we have a wave on a string. Okay, so this is called as mechanical wave. So we move our hand, okay, up and down. Okay, when we holding a string, okay, so we move up and down. So we see that the string will move in the wave direction. Okay, so the hand move the string up and then returns, producing a transverse wave that moves to the right. Okay, so when the string is length is over here, okay, and then we push up and down, okay, and then you see that motion going to the right direction. Okay, and then meaning that of course it had a speed to the right. Okay, and you see that the particle of the spring moving up and down following our hand motion. Pressure wave in a fluid also is a type of mechanical wave. Okay, for example, so we move piston, okay, to the right and to the left and right. Okay, so let's say we pumping the water, so we move right, left and right. Okay, it compress the liquid. Okay, so it produce the longitudinal wave. Okay, that moves to the right. Okay, so basically the wave will move the fluid to the right, and the particle of the fluid actually moving to the left and right, which is following the motion of the motion of the way we pump or we pump. Okay, so we also have a surface wave. Okay, example. Okay, so we have also that as a mechanical wave. Okay, the board moves to the right and returns, producing a combination of longitudinal and transverse wave. Okay, so basically you see that the wave is actually like that. Okay, but the particles is moving in the round direction. Okay, okay, so you can see that this is a Mexican wave. If you know that, so we was at this was actually okay, this was actually invented. Okay, it was actually invented during uh, the World Cup. Okay, the football. During that time, it was held in Mexico. Okay, so the people, okay, so going to make the wave around the stadium. Okay, so that is also an example of a mechanical wave. Okay, so the disturbance propagates through the crowd, but there is no transport of matter. Okay, it is actually the spectator, the fans, okay, moving up and down, following whatever is coming from the other side of that. So, but over here, there is nothing is moving except that our body. All right, it's just following the motion of that. Okay, so we also have a periodic wave. Okay, so when it is a periodic wave, we mention that it has to have the wave as a period. So to solve that, so we use the equation of V equals to lambda f. Okay, so this is I believe you have learned about this. So V equals to lambda f, where V is the wave of the speed wave, all right, the speed of the wave, and then lambda is the wavelength, and then f is the frequency. Okay, so we also have a periodic transverse wave. Okay, so where a mass attached to a spring undergoes a simple harmonic motion, producing a sinusoidal wave that right on the string. Okay, so actually, so the mass is going up and down. So we have the string there. So it's actually following what we did using our hand, right? Push it up and down, up and down, up and down. So according to that, right? You move to the uh, right direction. Okay. So that's what we call as the periodic transverse wave. Okay, so when we call that, we have the periodic waves, meaning that it follows a certain period, meaning that, so you see that that's the wave. Okay, so that's the wave. So you can draw that that's the wave. Okay, so this is a following another pattern. So you have period. Okay, so this is considered as one period. Okay, between there and there. So that's one period. Okay, let's say we drop something into the water. Let's say the water is inside a pond. So let's say we drop a rock to the water, and we see that there will be a wave that is made from the drop of that rock. Okay. Okay, so we can see that the crest. Okay, so this is the crest around that. Okay, so and that the direction of the wave actually moving towards those. I mean, when you drop the rock like that, and then it goes, it spread away. So that's the direction of the wave, where we can calculate the wavelength from that. Okay, so between, you can see that there's a like a ring. So between that ring is actually is uh between that ring is actually, you can calculate between ring number 1 and ring number 2. That's a wavelength. Okay, so which is the radial distance between adjacent crest or adjacent struts. Okay, so we call that that ring, the black ring, as crot, as crest, and then the white ring as a strut. Okay, so between white and white, considered as one wavelength, and between black and black, also considered as one wavelength. Okay, so this actually at a similar distance. Okay, so we also have the periodic longitudinal wave. Okay, so let's say we have a longitudinal filled with a fluid with a piston at the left end. Okay, if we push the piston in, we compress the fluid near the piston. Okay, compress the fluid over here. Okay, and then resulting to that, actually this particle over here will react to that. Okay, so when this is compressed, so because as you mentioned that, so whenever there is one part is compressed, so you need to actually transfer the pressure to the other part of the fluid. Okay, so that's why the other part you also need. Okay, so that's why we have the wave moving. Okay, okay, over there and over there. Okay, so we see that the blue, blue and blue, and the white, white and white. Okay, so between blue and blue, so we consider that as one wavelength, or we can also use that from white to white to actually calculate the wavelength, right? Okay, so this wave, okay, the wave we can describe that, the mechanical wave, we can describe that with a wave function. All right, so this is the wave function that we have y okay, equals to A cos kx minus omega t. Right? So where A is the amplitude, okay, and then A is the wave number, okay. So wave number is 2 pi over lambda, okay. And x is the position of the wave at the time we are measuring that. Okay, omega is the angular frequency and t is the time. Okay, and y is the wave function. Okay. All right, so we can plot the wave. All right, so in terms of a graph, so as you can see that, plot that into a graph. So it's like the experiment of the spring that we did. So it just follow the, let's say, the spring motion. Okay. So that's the shape. Okay. So you know, so it's follow the shape. So where we have the amplitude over there. So consider that from top to bottom. So it's actually 2A. Okay. So half of that is one amplitude, 1A. Okay. And then between, okay, between at the amplitude, okay, meeting another amplitude, so that's considered as one wavelength. Okay, so wherever it is, over here or here or over here, as long as it is the same amplitude meeting the next amplitude, okay, it's considered as one wavelength. Okay, so that's how we calculate the wavelength. Okay, so you need to remember that the wavelength is calculated based on the distance that the wave already traveled. Okay, so we have another type of graph, okay, which is based on t, based on time. So it is similar like the wavelength. Okay, so over here we call that as period. Okay, so if according to the t, then we call that based on period. But if according to the x, then we call that as the wavelength. Okay, all right. So that's the difference between uh, the graph of the wave for the displacement and also the time. Okay, so we have the particle velocity and acceleration in a sinusoidal wave. So you can see that. So this is how we have the acceleration and also the velocity. Okay. So at the top here, okay, we have the acceleration, okay, moving downwards. Okay, it will accelerate to move downward, and we are at the bottom. Then we have the acceleration going upwards. Okay, but both at this location, we have the speed as 0. The speed as 0. Okay, we look another one. So we have, so that's the top and the bottom of the amplitude. Okay, what about if the amplitude is 0? Okay, over here. So at this location, at here, and also here. So at the accelerations are 0. Okay, but we have the maximum speed over there. So we have the maximum speed, but we have the acceleration as 0. Okay. Okay, so we have another, if we are having two waves, okay, that are overlap with each other. Okay, so we have that one as t0. Okay, we mentioned that one as the t0 and another one at t equals to 0.5t. Okay. Okay, so but over here we still have the similar wave because we call that as having the same period and also having the same wavelength. Okay, as you can see that. So from there to there, it is at the same distance. Okay, so we have x over here where the wavelength is similar. Okay, so the wavelength are similar. So lambda 1 and lambda 2 are similar. Okay, so both of them are similar, so we call that is a similar wave. Okay, so we can also measure the speed of the wave. Okay, it is equals to square root of f, which is f is the tension of the spring over mu. Okay, mu is the mass per unit length. Okay, or it is the mass, called as mass density. Okay, so for example, we also have a transmission cable. So within the electrical cable that connected to between one location to another location. All right. So to transfer the electrics to our house. All right. So we have a large amount of mass per unit length and very low tension. Okay. So if the cables are disturbed, okay, let's say the bird landing on the dam, transfer travel along them at a very low speed. Okay, because it has a very large amount of mass per unit length. Okay, mean that for, let's say I measure from there to there, but the mass over here is very heavy. Okay, compared to the length. Okay, say the length is x. Okay, so it has a very big mass. So whenever you relate with this equation, so mean that you have a very big mu. Mu is very large, and then f is still similar. So when mu is large, so we have v as small. Okay, that's why we don't see much motion. Okay, much motion on the cable. All right. So that's why it is designed like that. All right. So that's why it is designed. Okay, so we also have power in a wave. So it is shown as the instantaneous power in a sinusoidal wave. Okay, the power is never negative. Okay, either at the so we have that when we have the wave. Okay, when we have the amplitude of the wave. So we have that over there. Okay, so this is the amplitude. Let's say that's the time. Okay, so whenever we are calculating that, okay, we consider that from the top to the bottom. Okay, so here is where P is max. Okay, so that's how you calculate the power. Okay, and then one more thing is that this from the period from here one time, okay, and then we have another time over there is considered one period for the power. Okay, sorry, t, so t for the period for the power. Okay, so that's the period for the power. Okay, so we can calculate the average power, okay, which is over here, by using this equation, which is half a of mu f. Okay, so what you learned before, omega squared and a squared. Okay, so that's how you calculate the power. So to get full power, So you just multiply with 2. Okay, so you get the full power. So that's the average power. And we also have the wave intensity. So where the intensity of the wave is the average power it carries per unit area. Okay, so if the wave spread out uniformly in all directions and no energy is absorbed, the intensity at any distance from r and distance r from a wave source is inversely proportional to r squared. Okay. Okay, so that's the wave intensity. Okay, so we look over here. Let's say we have this. Okay, so the source of the wave over here at the middle. Okay, then the wave spread out. Okay, at radius 1, r1, so we have the intensity as I1. Okay, and then at another radius, r2, which is greater than r1, the intensity I2 is less than I1. Okay, meaning that the intensity is related to the power, right? Intensity is related to power, where it's spread over a greater area. So this is the greater area that is spreaded. Okay, so this is small area, but this is the greater area. So you see that R1 and R2. Okay, so R1 is from that distance, and we have R2 from original source to that distance outside. So we have that R2. So that over this one, so this is R2 and this is R1. Okay, so the intensity is inverse to that. Okay, is inverse to that. So intensity, so you can call that is like that. Okay, so intensity is the function of R like that. Okay, so let's have a look at this example.
Example 15.5, we're told a siren on a tall pole radiates sound waves uniformly in all directions. At a distance of 15 meters from the siren, the sound intensity is 0.25 watts per meter squared. We'd like to calculate at what distance has the sound intensity fallen to a value of 0.01 watts per meter squared. So to solve this problem, we're going to use the fact that the sound intensity varies like 1 over the distance from the sound source squared. In other words, the intensity, more specifically, can be written as the power being radiated over 4 pi r squared. And of course, P is a constant in this problem, so we can take the ratio of I1 to I2 is equal to the ratio of R2 squared over R1 squared, where these R's are the distance from the source of sound. We can, of course, solve for R2 in this equation, and we get 15 times the square root of the ratio of the two intensities, and that's going to be 75 meters. Finally, we note that the ratio of the two intensities, I1 to I2, is a factor of 25, and that the square root of 25, of course, is 5. This means that the two distances, R1 and R2, must differ by a factor of 5, and 5 times 15 is indeed 75. And this ends example 15.5.
Okay, so it's easier so to solve this problem. So actually,
Calculate at what distance
use the
source
relationship
squared,
of I and
or
R. Okay. So basically, I is what we call that is equals to K R squared. Okay. So whenever there is 2K, where there is two different I, so you can remove that K. Okay. So when you can remove that K, so I, the ratio can be I1 to I2 equals to R2 R1 squared to R2 squared. Okay, so you can use that relationship. Okay, so and then over here you just plug in. Okay, plug in the value of one intensity and then you get the radius. Okay, so basically what you will,
These r's are the distance from 2 in this equation.
so like this one, so you have R2 equals to R1 square root of I1 over I2. Okay, and you plug in all of the values and then you get the answer. Okay. All right, so okay, so that's about the wave intensity. All right, so I think I will stop for that for today. All right, for this topic. Okay, so we will continue with this chapter 15 on the next Monday. All right, on the next Monday. Okay, so any questions so far? Actually, this for this topic, it is much more using a direct equation rather than solving multiple, multiple board diagram and so on. So what you need to remember over here is just the equation that is related to the wave. Okay, so you have the power, you have the amplitude, you have the intensity. Okay, so just need to remember all of that, the speed of the wave. Okay, and then the speed of the wave, you need to relate that with the and also the mu. All right, so that's the most important thing. Okay, so that's the key to answer the question that is related to the wave. Okay, all right, so that's about okay, so that's about it for today. Any questions so far? All right, if there is no question, so could you please turn on the camera so we can take our attendance for today? Okay, so remember that your test 2 will be next week on Thursday. Okay, so it will be on Thursday. And then you can ask me any question during next week during our tutorial session or also during the Monday lecture as well. Okay, by today, I finished gathering all of the questions from chapter 6 to chapter 12. So there's a lot of questions there. So you can choose whatever you want to study, right? So basically as I said, we have like test 1, we have 4 questions, right? We have 4 questions. So the last 2 questions will be from the chapter 11 and chapter 12. And then for the rest of that, 1 and 2 will cover from the chapter 6 up to chapter 10. Okay, from chapter 6 up to chapter 10. Okay. All right. So I'm going to count from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Give me one more shot. Thank you, everyone. Okay, have a nice day and enjoy the rest of the day. Assalamualaikum and bye-bye.
Thank you, Doctor.
Thank you.
You're welcome.